And this depends upon the material. For ABS, it will be 40%, and for PC, it will be 45 to 50%. So it depends on the material, but it has to be within the 50% of the wall thickness. And at top of the rib, it has to be between 1 millimeters and 0.8 millimeters with a minimum of 0.5 degrees on both the side. And this is because for the tooling purpose, the draft is very important. And the height of the rib should be 3 times the wall thickness, which is recommended, but sometimes it goes more than 3 times. But then we have to define the local thickening of 0.5 transition with the 30 millimeters in all directions. And coming to the radius or fillet, it has to be 0.2 millimeters minimum at the base and at all the side corners. Now let me sketch it and then just give you a brief idea on what exactly is the wall thickness and the rib to wall ratio, right? Just give me a second. Okay, now when I say part thickness, now I'll just define a part. This is just a cross section of a plastic part. And then this is the wall thickness. So this thickness has to be uniform throughout from start to the end. And sometimes some tolerance will be allowed like 0.1 millimeters, depending upon the material. And now coming to the wall, now when I create a ribs, so these are the ribs for strengthening purpose, right? Or for the stability of the part. So when I say these ribs, these thickness from this base, it has to be 40% of the wall thickness. And then this height should be 1 millimeter to 0.8 millimeters. And then this part here. So I'll just zoom in a bit here. So the rib looks like this. And then when I check the angle, so this is the draft. And this has to be 0.5 millimeters minimum. Oh, sorry, 0.5 degrees. And it is easy for the ejection of the tool. And now rib height. So these are the rib heights. And this height has to be at least 3 times the wall thickness, which is recommended as per the design guidelines. So this is the height of the rib. And now when I say local thickening, now sometimes it's not possible to maintain exactly the design guidelines like 3 times and then here 40%, right? So if I zoom in a bit, so here we have got ribs. And sometimes when I maintain 1 millimeters, and if the height is more, if it is more than 3 times, then here it will be approximately 50% of the wall thickness, or maybe sometimes 55 to 60%. In this case, there will be a local thickening. That means here I add a material local, and this thickening will be 0.5 millimeters, and then the transition of 30 millimeters. So from here and this transition, and then it continues with the material thickness. So from this to this transition will be 30 millimeters. And adding local thickness, then here I can maintain 40% of the rib thickness, right? So this is just a basics of design, plastic design guidelines. And then we have got attachment concept like plastic to plastic. There's like a welding pin between two plastic parts. If I take two plastics, for example, here I got a welding pin, and then there is one more material or one more plastic part. So there are two plastic parts, right? And then I need to connect these two parts. And then this pin will be welded. There'll be a device which welds it and then changes the shape of this. So after the final process, the part looks something like this. So here we have got one plastic part. And then this welding pin, it's kind of a attachment feature. And there the part is not separated. So it's connected between two elements with the pin welding, right? So this is about the plastic to plastic welding. And then we also got metal clips, plastic clips like snapping features, clipping house, And then draft is very important. Like the draft should be 5 to 7 degree minimum on the A side for graining, and then 5 degrees minimum shut-off angle. If there is a transition in the plastic part, for example, now this is the final part. Now here I have a transition, right? And when I see the core and cavity, so here we have got core and cavity. And this transition here, this is a shut-off angle between parting lines, right? Because there is a change in the shape. And when there is a metal to metal contact, this draft has to be minimum 5 to 7 degree when there is a transition. So this is a shut-off angle. And then 0.5 degrees minimum draft on B side for ejection. So in plastic designing, draft is very necessary. So whenever you design a part, the part has should eject easily with a minimum of the draft considered in the guidelines. And next way to define a parting line using a dry door direction with a sliding lines shall be defined. Now, if I take a simple example, this is a part. Let's assume it's a V-shaped plastic part, right? And then how my cavity looks like. So this is the cavity. Sorry, this is the core. And here we have got a cavity. This part will be fixed always, cavity. And then the core moves in this direction. So material is filled. And then the contact between these two metals, this corner here and from this corner, this is called a parting line. Like it's parting from the core and the cavity. And this is the definition of a parting line. And also it verifies clearance for the undercuts. And if you given a proper draft, then it's easy for the tooling where there is no undercuts. Now, for example, if you want to make a plastic part, which looks something like this. Now, if I draw a vertical line, now this part here is an undercut where this part cannot be manufactured because even if you do it, it will be fixed here and then the part will not eject. And also it's not a good design recommendation. So whenever you design a plastic part, make sure you give a minimum draft for the ejection. And the other side is easy. There's no problem here because there is a enough draft angle for the ejection of the part. So should be very careful in giving that. And next we got tolerances and RP system. There'll be a standard or a defined tolerances according to the part size. Bigger the part size increases the tolerance value, right? For example, if the part is 100 millimeters, then the tolerance will be, for example, zero point 0.1 millimeters. And if it is increased to 200 millimeters, then the tolerance will increase to accommodate the particular size of a plastic part. And then most important is a 3-to-1 principle. What exactly is a 3-to-1 principle? Now, if I take a part, sorry for my drawing, and there's a hole. Now, this part is in a space and it has got 6 degrees of freedom. It can translate in X, Y, and Z direction, and it can rotate along X, Y, and Z direction. So we need to arrest all these degrees of freedom, right? So first thing is a 3-to-1 principle. And this is a question often asked in interviews. Like what is 3-to-1 principle? Now when I fix the plane, so when I rest this part on the plane here, let's assume this is a plane. Now when I rest this part on this particular plane, then 3 degrees of freedom will be arrested. Like this translation up and down because it's resting, right? And then it cannot rotate along Y direction. If I assume this as Y, it cannot rotate. So this is 1 degree of freedom fixed, 2 degrees of freedom fixed, and also it cannot rotate along X direction. So there are 3 degrees of freedom fixed. And then remaining is it can translate in X direction, right? And then if I consider this as a Z direction, then it can rotate along Z direction. Now to fix the 2 degrees of freedom, we'll create one more plane here on the side of this part. So now this part is fixed. And now the rotation is arrested, right? And then it cannot translate in Y direction because here it is fixed. So here we have got 2 degrees of freedom arrested. So 3 and 2. Now remaining is 1 degrees of freedom. Now it can rotate along this edge. It can translate along this edge, right? Now I will define this surface or the other surface which is parallel to this surface. So once I fix this surface, 1 degree of freedom, that is this translation, is arrested. So this is a 3-to-1 principle. And then we use this in plastic in defining the features, how to fix the plastic part using this 3-to-1 principle, using the snapping features or some attachment features. So these are the importance of 3-to-1 principle. Next, I'll go through some of the applications of plastics in automotive. Now, this is just an example. What are the plastic parts used in an automotive or a particular vehicle? Now here you see approximately 105 kilograms of plastic used. And if you see here, most of the plastics which we have already gone through, like polystyrene, ABS, polycarbonate, PUR is a foam which is used in seating. And in total, there are 13 kilos only in seating. And the bumpers is around 10 kilos and etc. So you can just go through this. So the reason for this picture is like there are a lot of opportunities alone in automotive industries in plastic design. And if you have a Siemens NX knowledge, then you have got a lot of job opportunities also. I'll just brief you about the injection molding process. Now here, a raw material will be entered in the form of pellets. And then there will be a screw which is continuously rotating. And then it always pushes the grains in this direction. Just let me sketch. So there'll be a material flow in this direction. And then here we have got nozzle. It's like a spray, right? And then here we have got cavity, and this is the core. So the cavity is always fixed, and then core always moves in this direction. And now here, the gap you see is a form of a plastic. So this is the form we are expecting, right? And then when the raw material is put it into the hopper, this is a barrel. And then here we have got some heating elements. So here got one heating element, two, and then third heating element on both the side. So as soon as it is in a granular form, and then because of the screw continuously rotating, it pushes the material. And as soon as it enters the heating zone, it will be converted into a liquid form here. So by this state, it will be in a liquid form. And then because of the screw continuously moving, it will inject the material inside the core and cavity in the form of gates. And then here a material will be filled. And then here we have got a parting line. Now this is a connection between the two metal parts, right? Core and cavity. So here, this is a parting line. The part is parting between these two core and cavity. That's the reason it is called a parting line. Yeah, and then I'll just play this so that you can get a knowledge on how exactly the injection molding process takes place. And then if you see red, then it will be converted into liquid. And then once it is filled inside the core and cavity, it will be cooled, and after cooling it will be ejected, and then the part is ready. And what is the trends in the plastic industry? So what is sustainability? Now OEMs, or the original equipment manufacturers, assuming more responsibility for sustainability, like working with different suppliers on committed to low or zero emission waste initiatives, right? This is very important, because nowadays we are facing a lot of problems with the plastics for recycling, decomposition, and it's affecting the environment, right? So now plastic manufacturers are getting more responsible in defining the low or zero emission waste initiatives. And they are using also biocomposites and completely degradable polymers as a new alternatives. And then bioresins and eco-friendly plastic additives. As I said, plastic is getting more versatile because of the decomposition and also because of affecting environment, right? And that's the reason the environmental impact is more. And then the leading manufacturer are considering their approach to selecting the material which is of bioresins, and this is also gaining more popularity as an alternative, right? Because it is made of natural plant and vegetable extracts or renewable sources, which helps in green plastic through benefits and also easy for safer disposal, energy efficient in manufacturing, and also decreases toxic emissions, slimmer, lightweight parts and tools, right? So as hybrid and electrical cars are getting popular, lightweight parts remain a key focus for such automotives or aerospace industries or the medical OEMs, right? If the parts weigh more, then it directly affects its performance of the vehicle in terms of mileage. So in coming years, the plastic will be more slimmer, lightweight, and also some bioresins will be used for eco-friendly tooling. And then the high performance material. Now, increased demand for reinforced plastic. Now, what exactly is a reinforced plastic? It's a alternative to the metal materials, right? Because my metal weighs more, and then it also has some effects like injuries. It can cause injuries to a person. And then the plastics are the safer materials in replacing metal materials. And also most of the plastic materials with reinforced replaces metals to reduce the weight and also increases the performance of the plastic, and it is as good as metal. And that's the reason most of the industries are switching to developing the plastic material where there is a possibility to replace metal parts. And then responsible to recycle, so which is very important for the manufacturer, right? As it is getting problem for the environment, and most of the industries are designing a new product considering a bioplastic which is recyclable, and then also a good option for making a design recycle proof. And then of course 3D printing and production efficiencies. Now 3D printing is getting very popular in the plastic industries because using 3D printing creates or it develops a plastic parts which is quicker, and also we get a finalized product. And also the advantage is the cycle time reduces and quality remains the same. So this is a way to have more efficient production cycles using prototyping, which optimizes the product process, and also it increases durability and it is consistent also, right? These are some of the examples, like what are the trends in the plastic industries and what is the expected forecast in the plastic industries. If I just consider in 2018, the plastic usable usage is like $522 billion market value worldwide. And then in 2009, it was approximately 10%, around about 10% increase. And then if you see in 2025, the expected growth is increased to 721, which is almost 40% roundabout. And then in 2027, again, it's like 754. Now considered to 2018, it's all approximately 50% of increment. So there's a lot of opportunities in the plastic industries, and if you see, this trend is always increasing trend. Next, what are the job opportunities once you get a knowledge on plastic design and also Siemens NX software? So there are some of the possible job positions like CAD engineer, methodology engineer, technical lead, or even manager. So once you get a proficiency in plastic with Siemens NX, then you can easily get a job in any industries, because around you, if you see most of the plastic parts, right? The keyboard, mouse, computer, whatever parts, the mobile phone you are using, and also in automotive, you see all the parts which are made up of plastic. And also in automotive, sorry, in the aerospace, also when you whatever aesthetic parts you see, it's all made up of plastic. Not only aesthetic, still there are no-show parts also, which are called as technical parts. So you don't have to worry about the classes surfacing. This is like a complete development of the part based on the technical requirement. And then what are the companies who uses Siemens NX? Daimler, Siemens NX, sorry, Siemens PLM itself, Bosch, Nissan, Kasai, ABB, etc. And what are the list of companies? If you are concentrating alone in India, then there are a lot of opportunities in this field. Like all these companies you see here, Maruti, M&M, Tata Group, International Tractors, all uses Siemens NX in designing plastic parts. So for job opportunities also, there's no problem with the plastic development using Siemens NX. And if you also concentrating to search a job in outside or in other countries, there are a lot of opportunities also in other countries like USA, Germany, France, China, Japan, etc.